Welcome to the Advances in Data Science, as some people leaving. Advances in Data Science seminar series, and today we've got Marcel van Herk, who started quite recently.
A little over 4 years.
4 years. Is it at the Christie?
At the Christie.
And he's going to tell us about the very exciting field of radiotherapy, where there's tons of more data being generated, I think, and it's going to come, and we have to learn how to deal with that data. And Marcel's going to tell us about learning from every patient treated. Thank you.
Thank you. So just for my insight, I'm a physicist, and you are, on average,
Everything.
computer scientists, engineers, psychologists, I don't know.
Biologists.
All right.
Data scientists.
Okay. So I'm in radiotherapy, and I'll start out with showing you a little bit what radiotherapy entails. So radiotherapy is killing a tumor inside the patient with radiation beams, basically. So let me just move to this side. So you start out by taking a scan of the patient. Then some poor doctor has to go through the slices of the scan and indicate where the tumor is. Then some planner, see the slide is very old, you see the screen is ancient. The planner will design the beams such that the highest dose is delivered to the tumor, and that the dose to the normal tissues around the tumor is spread in such a way that it has minimal impact on the surrounding tissue, so that's an optimization problem. And then eventually the patient is moved to a big treatment machine where those beams are actually shot at the patient. And well, at first you can see that there is a little bit of a problem, because you're shooting with invisible beams at something that you can't see, because you can't see inside the patient unless you have a scanner. So, by the way, it's fine to ask questions at any point in time or interrupt at any point in time. So this is what a modern radiotherapy machine looks like. It's a bit like a Christmas tree with lots of stuff on it. So this big head is where the radiation emanates from. There are metal leaves in the head that can shape the beams to fit the tumor. And this thing rotates around the patient, and the patient is on the bed, and basically you can shoot beams from every side. Now we want to image, and I've been working on imaging in imaging all my life. So I started out with developing a detector to image the treatment beam many years ago. And later I worked on integrating a cone beam CT scanner. A cone beam CT scanner is a cheap CT scanner, and a CT scanner basically makes slices of the patient with x-rays onto the treatment machine. And I was visiting different institutes with David Jeffrey, and David is the one that came up with the idea, and I was the one that made it work. But so image guided systems are used now for image guidance, and that means that you can very precisely target the beams to the patient. And these treatments are planned once and delivered over 5 weeks or so. And the idea is that when you hit the tumor repeatedly, the tumor is not very good at repairing. The damage to the tumor goes worse and worse and worse, while the normal tissues kind of repair in between, and so that the differential damage to the tumor and the normal tissues is different. So fractionated treatment. So I worked on cone beam CT, and that's basically integrating a cone beam CT scanner with the system. So what happens, you rotate around the patient, take x-rays from every side, and then you do a cone beam reconstruction algorithm, and you get a three-dimensional image of the patient, which you need to compare to the planning image. There is a planning image where you say where the beams need to go, and there's an actual image which basically tells you where the beams go, and if they are not aligned, then you know that you have to shift the patient around. And that's a software that I wrote with my colleagues at NKI, and we licensed that to Elekta, which is one of the two big vendors of treatment machines. And the estimate is that more than 6 million patients have been treated with that particular bit of software, which is nice. So higher precision means that you have to use less safety margins. You can imagine that if you don't know where you're shooting, you have to shoot bigger. If you want to drill a hole in the wall, you don't know where it comes, you probably want to drill it a little bit bigger. So that's the same thing here. So increased precision means that you can reduce the safety margin, which means that you treat less normal tissue and that you can increase the dose. And we know that in a number of sites there is some evidence of reduced toxicity and increased efficacy Although, interestingly, that is never tested in clinical trials. There are no clinical trials to test newer equipment. It's just not ethical to compare a more precise treatment and a less precise treatment. Although, probably it's not that clear cut that it actually makes a difference, especially if you change multiple things. So the newest kid on the block is MR guidance. And this actually came from another Dutch center. I worked in Amsterdam before, and I did that work in Amsterdam. This came from Utrecht. And they had the crazy idea to integrate an MR with a linear accelerator. Now, a linear accelerator is an acceleration tube. It's incredibly sensitive to magnetic fields. And a microwave, which had magnetic fields. Basically, they're fundamentally incompatible. So there was a lot of work to make the shielding, active shielding, to make these things work together. So this is the MR coil, magnetic resonance imaging. The coil is at hi Alex, with liquid helium, very super cooled, so you have a superconductive magnet, and the magnet aligns the spins in the body, and you change that spin with radio waves, and you measure the resulting signal, and as a result you can get a signal which is related to the chemical characteristics of the body rather than the density. CT measures the attenuation to X-rays, so that measures the density of the tissue. MR measures chemical characteristics, and that basically means that the contrast is bigger, so you can see more inside the body, and that makes that people want to do more complex things, and that means that the workflows on these systems are actually something that needs to be worked on, but not something really to do with big data, but this is the newest step. Now, I mentioned that if you have better equipment, you can shrink the margins. And I said there is hardly any evidence for better precision, but there is a bit of evidence for shrinking margins, because these guys in Brussels, they were implementing image guidance with a certain technique, with implanted gold seeds, and they had measured all the uncertainties, and they calculated the margins with an equation that has my name on it, and they applied those margins, but then they forgot that actually when you reduce the errors in the physical side of the treatment, the errors in the biology might become dominant. And so they shrunk the margins to 3 millimeters left, right, and what they found is that in the original treatment with the big margins and less precision, they had a way better outcome than on the more precise treatment with smaller margins. So they went too small. And that is the biggest risk of higher precision, is that people overestimate the total chain accuracy. It's not only the treatment machine, and the patient is not a piece of plastic. You have to know about the biology, and if you look at a prostate cancer MR scan, very often you can see actually that there's a dominant lesion. This is the prostate. The dominant lesion, tumor grows out of it. Tumor, crab, things grow out of it, and they grow out of the prostate in the surrounding tissue, typically by 1 millimeter or 4. If you have a centimeter margin around because of the uncertainties, that's negligible. But if you shrink those margins to 3 millimeters, then all of a sudden you're going to miss a lot of patients. So it basically means that from physical accuracy, we have to start thinking about the biology. So this is the kind of stuff that image guidance does not solve. It doesn't solve that we don't really know where the tumor starts and ends. If you ask multiple doctors to outline a tumor, they disagree. And then obviously we have no idea what the ground truth is, because these patients are treated with radiation because we don't want to cut that tumor out, because it's attached or it's around tissue that you cannot damage. So we don't know what is the border of the tumor, except what we see in the imaging, and the imaging is not perfect, and that is reflected by observer variation, and this is an example where it's very small. Then tumors have these little things growing out of them, so there are tumor deposits around the tumor that are too small to be seen on imaging, and so we need to treat those as well, and that's based on statistics. We don't know for an individual patient where the tumor is, but we know for a population of patients that if we treat too small, that the tumor comes back. Then we have toxicity, because if we're shooting the beams at the patient, we want to avoid the structures that are the most sensitive, but we don't really know which structures are the most sensitive. And sometimes we just have it wrong, or we think that the whole structure is sensitive, while maybe only a part of the structure is sensitive. So these are all big data questions. Plus, classically, we get the data from clinical trials, a couple of hundred patients, and then we fit outcome models to the data from the clinical trial, and we think, well, that's it. But what we want to do is we want to bring this to steroids. We want to learn from every patient treated, and we kind of want to use all the data that is available, although obviously we never use all the data. So we want to set up a big data infrastructure, and that's what we did. And the first example that I brought is in prostate cancer. So in prostate cancer, you treat the prostate. There is a tumor inside the prostate, but usually there's multiple tumors inside the prostate. So the target is the entire prostate, even though the tumor is not the prostate. So this is called the clinical target volume. It moves around, and so we have all the image guidance. But in previous studies, one thing that we found is that if this prostate was shifted a bit by rectal filling, so the prostate is situated between the bladder and the rectum, then the outcome was severely affected. And we tried to model it, and we couldn't model it, we didn't understand it. So I was talking with my colleague then, Marcel van Herk, and said, well, maybe we should do something very simple. We're going to try and find out where the tumor is. So what we did is we took the scans of 100 patients. We didn't have a very large data set, 100 patients. And let me see if that runs. And then we registered those patients to the prostate. So we brought the prostate into a single frame of reference. We put all those patients on a big stack. And that allows you to also bring the planned dose distributions, how the beams are arranged, onto that big stack. So you get a movie loop of dose distributions. So these dose distributions are not true for the same patients, they're from different patients. And this was a randomization trial between two dose levels, so yellow is the low dose level, red is the high dose level. And you kind of think, well, the difference is going to be inside the prostate, isn't it? Because that's what the dose, where the dose level is the biggest difference. But actually that's not the case. So we're talking here about high-risk prostate cancer patients. And so what we did is we calculated, very simple, the average dose distribution of the patients that were controlled and the average dose distribution of patients that were failed. And lo and behold, to our surprise and delight, those average dose distributions were not different. Were not the same, sorry, they were different. So this is the difference of the average dose distributions, where white means that a higher dose leads to control, and black means that a higher dose leads to failure. But you see there's hardly any black. And strangely enough, this region is kind of 3 centimeters away from the prostate. And this is the obturator region, and the obturator region is actually, so prostate is sitting somewhere here. There are lymph nodes that drain the prostate, and the first level of lymph nodes basically goes to the obturator. So it's actually a known spread channel of tumor, but nobody really knew whether to irradiate it or not, and this suggests that indeed you have to irradiate it, although we don't understand it at all, because actually if you measure where the tumor is, it's all over the body. It's not only in that level, but it's still this in the data, irradiating this level, yes or no, makes a bit difference. And one other thing that we learned is that this region is often irradiated by chance, because the beams, the treatment is done in beams. It's not like surgery where you try to cut as precisely as possible. You have beams, so to get somewhere you have to go for other tissues. So if the prostate, which is sitting behind there, and the seminal vesicles, which we sit on top of, if they are in a particular configuration, so the beam can go quite high up, and if they are in other configurations, the beams stay quite low. So the dose at this level above the prostate, in a lot of patients, is quite high. The median is 50 gray, which is about 80% of the treatment dose. And actually, if you're above or below that median, has an enormous effect on outcome, which then brings you to the point, what does that mean? It's big data, it's correlation, it's not causation. So this is then very difficult to go further And so we are validating this. And then it turns out that if you validate it, then all of a sudden it turns out to depend on all sorts of other parameters. So this has given insight, but also a lot of questions. But I think this was the first time that somebody did data mining on 3D dose distributions, 3D dose cubes of these patients. So when I moved to the Christie, well, I thought, well, let's try the same thing in lung cancer. So in lung cancer patients, you're treating again with multiple beams, but the cancer can be anywhere in the lung. So it's quite different from prostate, where prostate is kind of always in the same place. So you see beam arrangements flashing by, which are all from different patients, but now they're split out. These are the patients that are alive after 1 year of treatment, and these are the patients that are dead after 1 year of treatment. And obviously you can't tell a difference by eye, but if you take the average of these dose distributions, and we had 1,100 lung cancer patients here, and that 1 year is about the median survival. Lung cancer is a horrible disease. People die quite quickly, and they're also in bad shape because of smoking and cardiac disease. And so we brought those dose distributions together with deformable registration, subtracted the average dose distribution. Now we found a black spot. And remember, if we first, on the other study, we find a white spot. The white spot means higher dose is good. Here, higher dose is bad. And now, where is that black spot situated? Oh no, sorry. Before I go there, is this significant? That's a problem, because we're testing 100,000 variables. We're testing every point in the dose distribution, so we have 1,000 times 100,000 parameters. So that's a big data question, and actually kind of independent from the neuroscience field, we developed very similar technology because we weren't totally aware of it. But this is permutation testing. So what you do is you just take the real dose distributions and then you shuffle the labels of dead and alive, and then you create fake differences, fake dose distributions, and you count how often the real dose distributions, their difference, exceeds the fake dose distribution difference. So it's a very simple statistical test, but to do it right, you have to count it only once. So what we count on is A statistics of the entire image, and we chose to use just the T statistics, so it's T max of the dose difference. T is the dose difference divided by the standard deviation of the dose over the permutations. And yes, this is better than 1 in 1,000 significance. So none of the fake differences exceeded the real difference. So this is very, very significant. Doesn't still mean that it means something. But here it is. So this is the T map. So difference divided by the standard deviation, minus 5.7. So lower dose is good, higher dose is bad, hence it's a minus. So it's almost 6 standard deviations out, this difference. And it's situated not in the middle of the heart, but really at the top of the heart. And that's interesting because lung tumors can be anywhere in the lung. So they can be on the left of the heart, on the right of the heart, on the top of the heart, the bottom of the heart, but they're always next to the heart because the heart is sitting bang in the middle between the two lungs. So you cannot spare the whole heart, but you can spare bits of the heart. And now if this is true, and indeed you only need to spare a tiny bit of the heart, then that is incredibly interesting because you actually can do that on a large number of patients. Problem is we don't understand the mechanism. So we say that this is true, we say that the heart is more sensitive at the top. But this could also be a data mining artifact because there are a lot of correlations. So correlation doesn't mean causation. For instance, if you have big tumors, draw a tumor in here, if it's bigger, it's bound to go to the middle. So dose in the middle is always higher with bigger tumors. So if you don't correct for that, then you're fooling yourself. You're just measuring tumor volume, and bigger tumors are worse, patients die quicker. So one thing is we need to correct for confounders. And the other thing is we need to understand the mechanism. And for that purpose, we are now doing a prospective study where we're measuring heart function on these patients that get radiotherapy and blood levels of troponin, and I don't know what all this stuff is called. But basically you can measure whether patients have heart disease, yes or no. and then hopefully we can find out what affects that, what the dose does in that region to the heart. But first we have to deal with confounding, and by far the simplest way is, okay, so we think it's the top of the heart, so from the data mining we define the region of the heart, which is kind of guesswork because we don't really know the mechanism. And then we define the average dose to that defined region, and we put that in multivariate analysis based, whatever it is, Kaplan-Meier, and Cox regression, sorry. And basically you correct for tumor size. So tumor size is incredibly significant. It's a very important predictor of survival, but actually the dose to that bit of the heart is as well, and the dose to the whole heart isn't. So that strengthens a little bit. And of course age makes a difference, and tumor stage makes a difference. So there are other variables that affect outcome. You'd have to do it multivariate, otherwise you're fooling yourself. So if you ever see a data analysis where tumor size is not included, then it's bad. So this is the survival curve. Lung cancer is a very bad disease. So after a year or so, half of the patients are dead, but there is a very distinct split between patients that get a higher dose to that bit of the heart and a lower dose to that bit of the heart. And the hazard ratio is 1.2. So that's incredibly interesting. But now I did something wrong because I did data mining and then I included confounding. I should have put confounding into the data mining because the data mining might show a region that is due to the confounding. And then, so that's what Andrew Gwynn did. Andrew Gwynn is my computer guy. Oh, sorry, first show the pictures. No, I first change the slide and then talk. Okay, so these are pictures of typical dose distributions that we were data mining, and this is the significant region. This was validated in an independent cohort of patients that were treated differently. So these are patients with small lung tumors, so you see the dose is quite a bit smaller, and kind of you find the same region, although you find an echo region somewhere else. And that's quite typical with data mining because if you want to treat a tumor that is on a particular place, then you're always going to put the beams in a certain way. So we don't think this is real, but obviously we cannot exclude that it's real. We think this is like an echo of the significant region there because of the way that these patients are treated and so of inherent correlations of the data. Okay. So how to deal with confounders? So multivariate analysis is good because you take the confounders into the analysis, but now actually our problem is a bit more complicated than that because we have 1,000 patients and we have 100,000 variables per patient, every point in the dose distribution, or depending on how big you sample it. So we have, so if this is the dose cubed patient, we have 100,000 times 1,000 numbers that we want to do the data mining on. But we also have confounding factors, and the confounding factors are the same. So the dose is different. The dose in the top of the lung is different than the dose in the bottom of the lung, but the age of the patient is the same in the top and the bottom of the lung. So Andrew wrote a beautiful package to do a Cox regression per voxel, basically. So he does 100,000 Cox regressions, create hazard ratio maps, and does permutation testing on the hazard ratio map. And basically what you find is a region over there, and maybe an echo over there. And then if I flip back and forth, you see that it's kind of in the same region, although it seems to have gone down a bit. So it seems to be that it's actually maybe this bit, less than that bit. So that's dealing with confounding. Now, in Manchester, we treat a lot of patients. The Christie is the only cancer center in Greater Manchester, so every cancer patient goes to the Christie, which is brilliant. Unfortunately for us, after they're done, they go back to their local hospitals to be followed up. So we can find out from Public Health England whether they're dead or alive, or from NHS, sorry, whether they're dead or alive. And we can find out from the doctors in the Christie what's written in the notes, but those notes don't go further than maybe a half year after treatment, because then patients are followed up elsewhere for a large part. So just a couple of months ago, we got access to Public Health England data. So we got access to death certificates and access to hospital statistics. And it took us several years to get access, which was annoying. But it's brilliant. So this is one abstract that we submitted to the ASTRO conference. It's the European Radiotherapy Conference. And Azadeh Aberfan, a postdoc in my group, did the data mining. And basically she looked at the difference of patients that died of cardiac disease and of not cardiac disease, where the death certificate is not brilliant. And interestingly, what she found is that was not only the region in the heart, the same region that we found before, but her data analysis, she actually balanced the groups on tumor size and on patient characteristics, because she has so many patients that she could create a balanced group where she comparing those distributions. Patients that have exactly the same characteristics, except one that died and one didn't die. The only difference is the tumor location. And that is very sensitive, and now she found a heart region, but also a lung region. And the heart obviously pumps blood through the lungs, so if you damage the lungs, we know from small animal studies, the heart basically starts to blow up because the blood vessels are blocked and the heart is just going broken. So it's not so strange to find a lung region and a heart region, although the data mining works per voxel, so per volume element, and it's not totally geared towards that. So actually, we would like to use more advanced methodologies where we're looking at connections between voxels, but we are not doing that currently, except by grouping them. Because you kind of expect that, for instance, the lowest branches of the blood vessels in the lung are the most sensitive, and that's kind of what you see because it's not where the vessels are broad, but it's when the tree has been gone down to its smallest branches where you find a sensitive region, and then why it's that region might actually be an artifact of the data. You have to have variability to be able to measure these kind of effects. So that was interesting. And then she did something else, which also is very interesting. Then she looked at patients that had heart disease, yes and no. Because of the hospital statistics, she could find out whether patients had been hospitalized for heart disease. And now something incredibly interesting is that, cardiac disease makes a big difference in outcome. Where if you have cardiac disease before treatment, there's a bigger chance of having it worse after treatment. But now what was very interesting is that patients that didn't have heart disease, their heart was very sensitive. Now, I say patients that did not have heart disease, that doesn't mean that they don't have heart disease. It means it hasn't been detected. These are lung cancer patients that have been smoking all their life. They have really bad hearts, and that's what now in the prospective study, that's what we find. The cardiologist that makes the scan says, wow, these patients have bad hearts. They should have been hospitalized long ago. But they weren't, because it wasn't detected, there was no event. So the heart is very sensitive in patients without detected heart disease. But in patients with detected heart disease before treatment, the heart is not a significant one, it's the lung which is the significant one. And that suggests that actually having a heart attack is positive, because all of a sudden you're under control and you're taking medication, and those medications might actually influence the effect of radiation. Obviously this is all inference, it's big data, correlation, not causation, but it's incredibly interesting, and this is a group of 1,400 patients, so it's fairly big data. Maybe not 100,000, but in radiotherapy, incredibly big data. So are there other signals that we can use? Time is all right. So image-guided radiotherapy I told about, that's good. And one of my students that I inherited from another supervisor who retired, she was going to look at the effect of setup errors, small treatment errors on outcome. And I told her, well, I don't think that you're going to find anything, because the treatments are incredibly accurate. So in some cases the treatment is a little bit off. We accept an action threshold. We accept that the treatment is not perfect all the time, just to save the amount of work And as treatment equipment gets better, we do that less and less. But so these are the residual errors in blood cancer patients treated with radiation in millimeters. So you see the scale runs from -5 to +5, and the action threshold was 5 millimeter, but that's done daily. And since the treatment is done over many days, it averages out. So the majority is ±1 millimeter. ±1 millimeter wouldn't make any difference, wouldn't it, if you treat with a centimeter margin? That's what we thought. But the beauty of these kind of shifts is that they are just an inherent flaw in the process. It's noise in the process, and noise is random. It's not correlated with performance status, not with comorbidities, not with tumor size, not with age. It's as if you're flipping a coin. Half the patient's going to go a millimeter to the right, and half the patients are going to go a millimeter to the right, to the left. And what she found very nicely is that actually patients where the dose distribution shifted towards the heart had a measurable worse outcome than where the dose distribution shifted away from the heart. So plus or minus a millimeter made a measurable difference in survival, which is really nice, and she won a nice award for that as best scoring abstract of 2,500 or so, which is not bad. Proud of her. So basically, the biology is the great weakness in radiotherapy. We know a lot of things about the physics, we don't know everything about the biology, so we need to work on that. So what we propose, and Garrett Price is working on that together with Quantitatively Finn, is to build some sort of formal rapid learning process into radiotherapy. So radiotherapy is governed by a lot of parameters. The dose threshold to the heart is so much gray for so much percentage of the volume. These are not well defined, these parameters, but you can change them. You don't need a clinical trial to change the parameters. People don't do that with clinical trials. If you find out from a clinical trial, from a publication, oh well, maybe we should think it should be a bit lower, or maybe it should be a part of the heart, people start doing that. Now what we would like to do is formalize that. And what Garrett did is he just ran an analysis, so based on the setup error data that it just showed, showing that if we collect data for over 4 months in our hospital and follow them up for 12 months, we can see the difference between a situation where this effect occurs and where it doesn't occur. And so, for instance, and we could solve this, for instance, by changing the dose constraint on a bit of the heart. Say, we can spare a bit of the heart more, and we think we can measure, we can detect that in a very short time. But it's not easy. You need to develop the statistics, and it's also, this is kind of a alternative to a clinical trial. So we were struggling whether to make it a clinical trial or an observer study. We just don't really know yet. So we're struggling a bit with this, but it's great that it's possible. So another thing that we're looking at is we have all these images, and those images don't only tell us how the treatment was done, they also tell us things about the patient. So this is a bit of a new line for us, and this is imaging biomarkers. Can we tell from routine imaging how the patient is doing? And we like AI because basically with AI you can, for instance, segment a certain organ, measure its volume, that kind of stuff, and you can do that on a very large scale. And so there are a lot of biomarkers that are possible. And Andrew Green started with sarcopenia. Sarcopenia is muscle wastage. And basically, if you have an old and frail patient or a bodybuilder, you see the difference in the muscles. And so if you have sarcopenia, the muscle compartment shrinks, and this is on a CT scan. And actually, the muscle also becomes less dense because there is fat infiltrating into the muscle. And many people are looking at sarcopenia, but they're all doing it by hand. They're measuring these kind of scans by hand. So if you use a CNN to do that, then you can do it on larger cohorts. So that's what Andrew started doing. He used transfer learning, which is interesting. So transfer learning basically means you take a network, VGG16, and this network is made to differentiate boats from cats and dogs. I don't know what it's made for. So this would detect a dog and say this is a dog. But we don't want to see what the dog is. We want to see where the dog is, where the muscle is. So he cuts off the dense layers. I don't know, all of this stuff. He added extra convolution layers, transpose, skip connections, all that kind of stuff. And basically then retrained the network to do segmentation on the sarcopenia patients using about 200 patients as input, which is quite a small amount, and getting basically a segmentation network. And the result is a fairly nice segmentation result, with like a 95% success rate. It's not 100% there, but it's good, and it's very fast. Although we need to do a little bit of work because we are only doing a single slice, kind of for standardization. And what that slice is, we still need to write a network to find that slice. We've now done that manually, which is like 5 seconds work per patient. But still, yeah, that's a bit of a thing. Yeah, question.
Do you know how this sort of segmentation lines up with the manual one?
Yeah, well, it was trained on the manual ones, and we have the data very well, but I don't know it by heart how well. And then, lo and behold, sarcopenia correlates with outcome. And this is the first study we did with only 100 patients. We now submitted studies with a couple of 100 patients, and it's very predictive for outcome. And actually, so transfer learning is good, but this measure is also very good because this could be an alternative to something like performance status. Because performance status is ask, can you walk up the stairs without puffing, or that's very qualitative, while this is very quantitative, and it's beautiful. And another example is of course cardiac health. Well, how do you measure cardiac health? One way of doing that is looking at plaques in the vessels, which are indicated by calcifications. Old plaques become calcified. So go and look in CT scans where the calcifications are. Now, normally it's very small. Normally you do this on specific scans made for this purpose. But we are doing it on 4D CT scans made for treatment planning. 4D means they're a movie loop over a respiration motion. And we just wrote a very simple image processor. We should have done it with a neural network, but we didn't. We just wrote a simple image processing algorithm. And now, because we have 4D data, you can do fun stuff and look, for instance, over the respiratory cycle, which image where you detect the calcifications, in which image the amount of calcifications correlates best, for instance, with myocardial infarction rates and with comorbidities, and it's very beautiful that you see that this clinical correlation peaks at inhale and exhale where the image quality is the best. So you're measuring image quality with a clinical correlation, which I find kind of funny. And then she takes the average of these 2 points, and again you have a predictor which says something about survival. So another biomarker. Still early, but it's very nice. So what goes well? Well, we have access to almost all patients treated at Christie. We have an umbrella ethics in place, which basically means that if we want to do a new study, it takes a week to go through the process, which is great. We can access all the images that are in the Christie and are allowed to do so. We have survival data of patients, and recently we just got the public health England data, but that was a nightmare to get to, And so the ethics basically means that there is an oversight committee, and there's little proposals, and they're discussed twice a year with a committee, but they're approved just by email in a week's notice, and that's nice. And also the same ethics has been implemented in other trusts, which is also very interesting. So they've taken our ethics, replaced Christie by their own name, and then it went through ethics, which I think is brilliant. So we should maybe do this also in other hospitals in Manchester. What can be improved? Well, outcome data is not so good. Also the public health England data is not so good. So there is a big drive to develop patient-reported outcomes with apps and stuff. Physician-reported outcomes are also not very good. It's all free text, so if you want to go in and interpret it, you basically have to write text mining or have a poor MD student go through all the notes. And it's really difficult to access data in other trusts. We collaborate with leads, and again, it took us 2 years to get to that data, which is horrible. So we're thinking about solutions, and that's maybe something to discuss offline. And one thing that is interesting is coming up to is maybe to implement wearables as one form of measurement of outcome. For instance, heart rate is a very good indicator for cardiac health and activity. So that brings me to my conclusions. So there has been a revolution in hardware and software that has given us an unprecedented physical position of treating these patients. So that means that now the physics is no longer the problem, the biology is the problem. And there are many biological uncertainties, and I showed you like contouring and outcome and toxicity. So the last decade, we and our colleagues started the data revolution, I think, which allows us to learn from every patient. The methodology is brand new, but rapidly developing. Christie has some data on many patients, but we don't have detailed outcome data, so sometimes we need to infer the outcome data. But all in all, I think that big data analysis starts to provide clinically actionable insights. That's a nice word, isn't it? Actionable. So, and this is obviously not only my work, it's a whole team. We have a very social team. This is our lab meeting. We are crammed together in a tiny little room. Our Christmas lunch with lots of booze and lots of fun. And no, that was it.
Great. Questions?
Yes, please.
I think you mentioned a few times that with these radiographic machines, you don't really do clinical trials?
Well, obviously you do clinical trials, but you do clinical trials on the big questions. Should we combine radiotherapy with this drug or that drug? And they're incredibly hard to set up, and incredibly expensive, and incredibly slow.
Okay, so for these changes where you don't do trials, do you think that's overall a positive?
No, I think it's a negative.
Okay.
Because we don't know. You know, we could be harming our patients by changing our process and not really realizing it. And what we're doing with the big data is it's kind of finding situations where indeed you could find those differences. Overall, it's better to be more precise, but if you are overconfident, it could be worse.
So I had a question actually. In your feature detection between the two classes with the images, you did these t-tests and looking for regions. Do you ever find regions where up and down is bad and there's a sort of sweet spot and the distribution is different in the positives and negatives?
Well, often you kind of have, and Alex knows that very well, because he did another bit of data mining, which I'm not talking about yet. But obviously, often dose is somewhere in one place because it's not in another place.
Yeah.
So you kind of expect a positive and a negative, and obviously you're kind of looking for the positives, but it so far it seems to be reasonable that the negatives are there, but are in places where there's nothing. You know, maybe close to the skin.
And the CNNs with transfer learning, have you gone back to those image cases and just looked for attributes in neural networks that distinguish between those?
No, we didn't do that. It's interesting. So I supervised a bunch of students together with astronomy, and they did that, and they were very happy that they found some weights which are positive inside the body rather than outside the body. So I'm not 100% convinced that gives very clear insights, but you know, we are just starting on that path, and we're learning quickly. But yeah, it would be fun to work with other people that have a lot of experience and see if we can improve this and understand this better.
So maybe a sort of a follow-up question to that. So in this case, for the transfer learning, you trained on, you know, dogs versus cats versus boats.
Yeah.
Do you think it would make sense to, because there is a lot of X-ray imaging available, maybe not always necessarily from the lungs. Do you think it would be sensible to do a big training on some of them, so like X-rays pictures, and then transfer to the lung X-rays?
Yeah. So the main that obviously that is something to be said for that. The obvious problem is train against what. So what do you want? What is the problem that you want to solve? And I'm not sure if you're aware of the AI literature, but there's one publication about using neural networks to solve jigsaw puzzles.
Yeah, I think.
So you can make jigsaw puzzles out of images, and actually we have one abstract gone into the radiotherapy conference where one of our students who just started, PhD student, did that, and so we use it because that's you make the jigsaw puzzle yourself, so you know the answer, so you can train on lots of data without needing well curated data, and then retrain on a well curated small data set. So that is a possibility, and obviously, finding CT scans of 10,000 lung cancer patients is not hard. But finding outcome data on 10,000 lung cancer patients is hard. And with segmentation, it's really a problem because people draw quite differently.
Question. I was going to comment on another thing, but your last comment is it related to GANs, generative adversarial networks? Because people are using the concept of GANs, to increase the training data that they have. Problems with medical field is always the small data set compared with the VGG net that you talked about was trained on ImageNet, which has 14 million images. So
you know more about it than I do.
So that's a problem. With medical images, you can probably use GANs to train two networks, one to actually generate new examples, and one to tell whether these new examples they look quote unquote all right or legitimate or not.
Yes. So the obvious application there is to create new images, and indeed we have one postdoc who's working on that with students. And he's trying to create fat suppressed MR images out of non-fat suppressed MR images, and he's using GANs for that with reasonable amount of success. But in a way the sky is the limit. There are a lot of possibilities, a lot of different techniques.
Very promising approach. Actually, I wanted to ask about something. Like when you described the unit, we actually used it. In a competition on a website called Kaggle. I'm not sure how many people are familiar with it. It's very, very famous for hosting machine learning competitions. And there's, I think, a hospital in the United States who, in collaboration with some universities and some companies, they had a competition for 2 months for what they call pneumothorax segmentation. So these are lung
collapse.
Yes, and they had all these images of CT scans of lungs, and they had 2 months of people working very hard on trying to win this competition. It had like a $20,000 prize. You have hundreds of teams participating, and of course, if you participate, there was an associated conference with the task. Then you get to write a paper about your work, and to get published in that conference. So I think that was a very good way to jumpstart work in a certain direction.
So I do nothing else than writing software, thinking about patient movement, and I'm a physicist. And neural networks. So all these things that I do a lot of work for are tools for me. The important thing is the patient. So actually, this would be a brilliant field to collaborate with groups that are really good. I'm not good at it. We're just starters in neural networks, and we're learning quickly. But I think this is definitely a field where we should collaborate. And I know that these kind of competitions are also held in the field of medical imaging, and also in segmentation. But again, for us, it's from us, the application is more important than the underlying network. But obviously, the underlying network needs to be good.
I was just thinking, if you held a competition was
we can do that.
You will get a lot of ideas from
Andrew run a little AI school in radiotherapy, and it's because it's such a small field. There's not so many people working on it, and it's not like that at all with hundreds of groups. But definitely, it's something that's interesting to think out and see whether we can do that. Also thinking about putting something in the blue dot.
Related to that, the Turing Institute run data study groups, and we can host these data study groups. There's a bit of funding for that. So if there's a way of dealing with the ethics of opening data up to a sort of controlled group of people, there may be opportunities to get people together to do some
Yeah, no, definitely, and actually there is some public domain data as well. The NIH, sorry, too many abbreviations, in America hosts quite large databases. So for most of our student projects, we're using those databases because just of avoiding the issues with ethics.
Okay.
That's
All right. Should we thank Marcel once more?